fast. The moment you talk about cache coherency, even though you may have 75 CPUs, only one guy can modify a variable. It is a serialization. You have five writers, that 5 writers cannot do all at the same time. You are serializing whole cloud or whole machine. But the moment you do that, paradigm shift in your programming, the hardware is linear babysit, hardware can be lightning fast, and everything can go in parallel. Right now, our programming makes fastest hardware go slow. And we just talk about all abstractions, right? So let's get on to the details. So really, what's the root cause? Where the cache coherency requirement is coming from? This is the software developers' problem of not doing truly parallel programming, doing the same mode, right? Very comfortable, right? Or the hardware guys are wondering, well, this software guys say they are going to do, but I cannot believe I need to make all the previous software to run on the same hardware, so they are over-designing. I don't know. So that's why we are going to look at it, right? Well, but message passing is not a cakewalk. It needs moving packet data around. You showed me the worm, right? So moving data, won't it be a lot of overhead? We are talking, yeah, you are saying that only one variable can be modified in 75 or 1000 nodes, so you are serializing, but then moving packets in 75 node system, when they talk about it, one CPU able to send to 75, at the same time all the other 75 able to send, they're talking about 75 into 75 crossbar, is it not that complex? Won't it be lots of overhead? So I'm going to do the same old because that shared memory paradigm is just write, read, no moving data around. So I'm really making the hardware guys like easy, maybe under thought process, right? How many of you agree with this thinking? Shared memory, read, write, no moving data. Message passing, moving data, right? Okay, so you are all 74 CPUs. We don't want to just read, we want to write also, right? So the question is, he's already 40 files ahead. He's already 45 seconds. So what he's saying is, well, shared memory is not that easy. You are saying there is no moving data, but if one guy writes out of 75, and if another guy needs to write after that, the data has to go from this guy to another guy. Even in shared memory, what he's saying is, possibly that complexity is there. So possibly in shared memory, the complexity is there also, and you are also serializing the machine, you are doing worst, just because software guys are not moving anything. They are doing the same old. True, very true. So you have written something for a single processor. When you want to do multiprocessor, if you take the same thing and put it in, what he says is, even if it is shared memory, the same problem is going to be there. You are not solving anything, right? And you cannot expect magic. So when you say shared memory means just, what do we do for moving this? Oh, here. This is what it is. Yes, right? Yes? Yeah, I know. What did he do? Tell me. Share. Don't keep it in the cache. I see. Okay. So yeah. So when you say shared memory means just read or write, no moving data around, right? And this is him. Yeah, right. That's what he said. He pretty much said, yeah, right. Do you mean shared memory? That's what I'm thinking as a software engineer. Shared memory means memory is there, cache is there, fast read, write, no worry. Message passing. But what he's saying is, just because the word message passing is not there, the problem did not go away. When you have many processors, one guy writing, another guy writing, the problem automatically is there, and you made everything hard. Okay, good. So, am I speaking very fast? No, right? Okay, good. Listen fast. Okay, so Why do you need, okay, now let us go back. We all agreed that just because we need to share, the problem is there, correct? Forget about shared memory or message passing. Just because there is sharing, the problem is there. But let us look at this model, right? You have one core, one NIC port, and one thread, POSIX thread fitted in that core. It has its own local variable, and it is doing run. We will talk about what is run to completion. That's a DPDK model where one CPU, one port, it just runs to completion, meaning receives, processes, and transmits back. It doesn't work with anybody else. It's a loaner, and it's a fast loaner. And in this case, my question is, if enough budget is there, he can do all the processing himself. That's called run to completion. So my feeling is, if that is the case, no need to share data, correct? In a way, at least at the lowest level, driver level, maybe higher level, yes. So let's quickly talk about DPDK. I just introduce the word DPDK. What DPDK does is basically the whole topic you can name it as bypass, bypass, bypass. Because bypass everywhere, right? Like old McDonald's song, like that bypass here, a bypass there, a bypass everywhere, a bypass. That can be the topic because DPDK does what? Bypasses the kernel, right? Because a lot of disadvantages bypasses the kernel. Cache does what? Bypasses the memory. And then write back cache does what? Bypasses write through concept. And then posted buffer does what? It is bypassing the whole memory. We'll talk about it. But the point here is, as I said, receive, process, transmit, all able to be done by one core if you have enough budget. And it is possible. And that's what DPDK does. And that's why we are able to get 30 times performance, not 30%, 30 times performance in the Linux kernel. Okay. And you all know that it is, that is quickly going to go through those files. Okay. So how do we really do it? What are the benefits and how do we really do it? We avoid context switch overhead because we do polling and we do ISO CPU type of things, and then no kernel user overhead because we keep the whole thing. We unbind the kernel driver and we bind it to the user driver. Right? The moment you bring up the Linux, you will see if config, you will see all the network. But the moment you bring up DPDK comes and knocks the kernel driver goes away. Now if you do if config, you will not see the driver. But DPDK takes it and then it does the polling, right? So, and then again, core to thread scheduling, overhead is not there because affinitizing, and then no huge page overhead because of the 4K, we don't have, we use 2 meg, and then lockless intercommunication, right? We talk about all this, so many cores managing. In fact, if you look at the DPDK documentation, the concept-wise, they use the words NQ and DQ, more like a message passing, right? If you implement that in a way, without needing cache coherency, you can achieve that. Because you do that lockless include and EQ, and then bulk mode IO calls. We'll talk about that. So these are the key core concepts. How many of you are already familiar with these concepts, right? Possibly new, not new to you. Okay. With that, see, that's the model which we said. One CPU does whole, receive, process, and transmit. And then next one, can you help me please? This whole thing came up. Here I see different things. I think this may be the second screen, right? I think we have to do that. We have to go like it. Maybe I think I put my glass. I'm trying to act young. Okay. So you saw one model of DPDK. DPDK supports 3 models. One is run to completion, which I showed you, right? The second one is spread if the pipe is fat, spread it through hardware RSS and then assign different cores for different queues, basically one core, but now into different smaller queues, and then assign one core. Again, it is individual, no sharing, right? And that's what the second one is. Okay, very good. And you will see that. And then this is the third one where one manager who doesn't do any work, he just assigns the work to the worker thread. So that is the pipeline, right? So if you see here, he is handing out packets. So in that case, there is whenever there's a manager, always overhead. Pipeline comes in, okay? So my manager may be on the line listening anyway. So he this, right? So this is what this model. So it is a pipeline model that needs sharing, pretty much. Looks like, okay? So let's stick with that, and then let us now zoom into the implications of sharing and the drawbacks of the existing same old code. How can we map our software variables to hardware infrastructure? Right now, this is a software block diagram. We talked about thread, local thread, and then we talked about shared data. Now we are going to do mapping, right? Your software. So this is a hardware block diagram. Right? We talked about the Jolna bag. This is the Jolna bag, and this is the shared memory. We are all see the right. So how do you map that? How do you map your software to the hardware? Right? Very simple, right? You map the thread local stuff here. You thread the shared memory data to this cache. Correct? Now quiz time. Quiz time here. Okay. What is the quiz? So let's say I'm a hardware engineer. I come to you and I'm asking, hey, I have a limited budget, right? This is the transistor I have. Now you are a software engineer. Tell me, should I increase this? If I do that, you are going to get less of this. Or should I increase this? In that case, this is going to be less. The reason I'm repeating this same thing 2 times is this. I work with a lot of customers. Now they get the NIC, they use it, and they find the traffics are not going too much, and then they call, say, hey, you have RFS, I can use multiple queues. They get excited, right? But the question is, if you have the same road, and if you are dividing 4 lanes, you are visualizing there are going to be 4 cars. No, it is going to be 4 bicycles because same road, right? Right? Same way, I'm saying same transistor. What's the trade-off? So tell me, if you are a software engineer, if I'm asking you which one you will increase. You want me to increase this or you want me to increase this? We just saw the sharing, we saw the local storage. Tell me, and then why? Yeah, that's the engineer answer. Okay. So you know your application, tell me.
Repeat his answer.
Yeah, if the locality can be really enhanced where each one of the code does what it has to at the local level, then I need much more local memory and very little shared memory will do.
Okay, very good. So it all depends on the locality. Very good, fantastic. Give me a clap again, Dave. So what about locality? So that's the question. So let's look at what's the locality network processing, right? Network application data plane. So what do we really do? This is what we do, right? Packet sorting, forwarding, right? What we do is you look at the header and then you do something and you right away sprint to next packet. And when it is a line rate, you do at fast rate. Are you standing at the same packet and doing? Maybe in deep packet inspection you are doing, but in a regular forwarding application, you spend like very little time with one packet, right? So you sprint from packet to packet to packet. So in that case, what is the locality? Not the same packet with fast line rate to sprint from one packet to another packet very fast. So how is the temporal locality doing in network applications? So if you design, so the answer, so what's the answer? Answer, I'm a hardware engineer, I want the answer. You want this larger individual cache or you want larger shared cache? You know the locality of your application. I understand locality is what is important, but you know that, huh? Dynamically adjust it. Aha. You should design hardware and then you should ask. Huh? Larger shared. Very good. How many of you vote for larger share? Okay. Oh, you don't believe in your ability to localize your program? Okay. So good. But they took. So what's the other half? Who are not agreeing for that? Who will not lift your hand, whatever I say? Okay. So small. So what about locality, right? So which means networking application there's not much locality. So if you have smaller, so if you ask for larger shared memory, what is going to happen? It's a trade-off, right? We have fixed budget. You are asking larger shared memory. You are going to have a smaller individual memory, and you already don't have locality. And now you made your individual caches small. So every time it is going to be individual local cache? Miss. If your program is already not having locality and you made from the previous generation, the next generation, now you made it small because you asked me to make the shared one big, and now you made yourself the individual cache smaller, and your program is not locality, and pretty much that means it's going to be missed all the time in the smaller cache. Smaller cache is 4 cycles only. You get the data. Now you go all the time to the larger cache which you asked, and since it is larger, now it is going to be slower. Now you come 95% of the time to slower. Now you are worse than where you started, right? You better watch out what you ask for, right? So what do you wish for now? Anyway, you wish for the break, huh? Okay, good. So that's what we talk about, right? If you are going to have all the time missed, then you are going to go all the time to the 40 cycles. This is a 4 cycle. You are going to go all the time 40 cycle. You made it big. Now possibly it's going to be 60 cycle. So so it's better to ask for, I don't know. You tell me. So your answer, what is that? Okay. So now, now let us look at. So now we saw that we quickly went through the characteristics of your load and then the implications of larger cache and smaller cache. Because now when you look at the data sheet, you should now give attention. Okay, this guy has small. So now you will be able to think about the discussion what happened here, right? Hopefully. Okay. So now let us talk about that. This is the core. You are doing a packet description, read and everything, and let's say if it is hit in 4 cycles you are able to get. So you remember we saw this read, process and write within one processor doing possible if it is that fast because it's able to read the descriptor in 4 cycles. Possibly it can do the processing and transmit. So possibly without dropping packet you can do it. So read is really good, right? Read the cache is benefit read, correct? Looks like it, right? Miss, I'm asking you any miss here. What about the first read that may cause miss? Because the caches are going to be useful only when the second onwards, right? What about the first one? It is go to the L3 and you do only one time use our packet and you move on. So pretty much even in the cache, looks like if you do without doing anything specific in your software, you are possibly not going to have what you want in the L1 data because you don't have data locality. And it will give improvement only if you are doing same data operation again and again. But your packet processing, you move, right? So what good is your L1 then? So that's how you are operating, okay? So even if you have good L1, that's why what we do, when we go and read, we don't read one, we read a bulk. We read a bulk, thereby we brought 4. We hope that at least you will process consecutively what you are reading. If you go for one at a time, then the size of the thing will make it miss. Then again, next time when you go, again you have to fill it up. That's why we do that bulk. Did you get the logic behind where you are through your software programming? You have to consciously improve the locality. If you don't do, if you just go to the socket, get one packet, go to the socket, get one packet. That will be cool programming. Same code you can port, but then it is going to be cache will be cold, cache will be cold, cache will be cold, right? So that's why DPDK does that, and you have to do that in your applications like that. How many of you are doing that? Okay, so cache. So some of you may be like completely way up in the software. So quick 2 minutes. What is cache and cache tag? Okay, so if you see this is a cache size and this is a memory size, and let's say 4:1 is the size ratio. The first line of this can be occupied by any one of them. So there's a directory tag which will tell first one of them is it occupied by that one or this one or that one or this one. So pretty much the tag is more like a hash to tell. And so if you're running here and suddenly if you move here, so things will be evicted and then others will be brought in. So that's the cache concept, right? Are you going forward? So that's why we bring. Now even if you bring all of that, right, but let's say your program is not local, sometimes it can happen For example, if it is a hash table references, is that local? Is it localized? No. You really don't want it to be localized, right? So in that case, even if you write very consciously to bring, and then your hash table lookup is all over, then again you are going to be sold cache, right? So I am telling you, possibly you should, this is time to bite the bullet and go back to message passing. Even the shared memory with the existing programming paradigm, the hardwares are really bleeding and begging. Yeah. So let's look at write now. We just started a read, let's look at the write. So anyway, can you come here quickly? A quick demo. We said cache reading takes 4 cycles, right? The smallest cache takes 4 cycles. What about write? Let's say he has to, I have to read it from him, right? I'm a CPU, he's a local cache. I'm going to read it from him. It takes 4 cycles. So I need to wait till he gives, takes 4 cycles. But let's say now I need to give him, right? I am the CPU, he's a cache. I need to write. He takes 4 cycles, but I have the data. I need to give it to him. Why should I wait for 4 minutes? Can't I, four cycles? Can't I just leave it here and run and then let him take 4 cycles to take it himself? Do you understand what I'm saying? Thereby the CPU is really, yeah, he's taking 4 cycles, but I'm now gone and doing another program. That's posted right. So we're talking about 0 nanosecond CPU doing right. So keep that in mind. Thank you, sir. I appreciate that. Now keep that in mind. So that's the posted right we're going to talk about. Okay. So now write has multiple flavor. We are going to go through and talk which about. Okay. This is shared memory. This is cache. So write through versus write. So whenever CPU writes, it writes the cache. Do you want it to be writing at the same time to the memory, or you want to write it to itself and keep it? So I have my local cache. I am writing. You cannot see what I am writing. Do you want me to write it and keep it here itself, or when I write it anyway, it takes 4 cycles or 0 cycles, and then it takes 40 cycles for me to write it on the memory also. Anybody can see. Which one is better? 74 people are able to see right away once I write it in one case. Another case, I am fast, but I am only writing to myself, but none of you can see. You have to come and snoop me. You have to come and snoop me. That's going to be delay when you started writing. But when I delay my writing from 4 cycles to 40 cycles, then you are all able to see. Then that's a benefit of you seeing that. Then you can write right after that. So which one you prefer? So that depends. Again, engineer answer. But the description of write through is the first one, right? Is it clear? I want you to understand this difference clearly. What is write through? Write through means I am not just writing to memory, right? Not writing to my local cache. I am writing to the memory also right away. So that's a write through. So what's the time it takes? Memory time. So you want to cache. What's happening now? We said read, first read happens at memory time, right? And then if you go all over the place, cache, hash table and all, locality gone, memory time. Read, memory time, memory time. Now write, if it is through, memory time. So what are the caches are doing? Sitting and getting warm in their chair, not doing anything, right? Correct? So what about multiple writes? If you do, say a cache line is this big, you may be writing here, you may be writing there, different variables, but they're all in the same cache line, but every time it is going to go to memory. So each cycle is now happening at what speed? Memory speed. Wonderful. And if the memory is in the other socket, God bless. Right? You know what the other socket means, right? Okay. So in write back, this guy writes it in 4 cycles, boom, he's done. He doesn't need to go all the way, so he is not waiting for 40 cycles. So writes are faster and multiple writes, very fast, right? So reads depends on how your locality, but writes are at least 4 cycles. But the problem is everything is now within him. Nobody can see. Correct? So if you want to do read or write, you need to come and snoop me, right? Lot of snooping going on. Okay. They're not talking politics here. Okay, good. Now let us write through first. Now for the second. Now see, we talk about when you do programming, message passing programming, all over the packets are moving, right? Whereas you thought in shared memory, right? We just saw things are not that fast. It's like a slow only. But at least there is no packet moving, correct? That's what we thought. Now let us look at really there is no packet moving, or in this also, as the gentleman said, well, the moment one guy writes, if somebody else wants it, packet has to move, whether it is shared memory or not. Correct? He said that, remember? Now we are getting into that. So let's say this guy wrote it. In write through, it is available here. So for the second guy, when he wants to see, I told you, right? Everybody is able to see. So he's able to see. So if it is already in the cache, he will read it from the cache. But if it is not in the cache, since he wrote it in the shared memory, he can get it from the memory. Simple design. Simple design, it is going to be slow on misses, but simple design, right? Write through, that's the benefit of that. But what happens at write speed? Or with what speed, right? Which is happening at memory speed, we saw that. I mean, it is repeated write, it is going to be slow. Now, let us look at write back. In this case, what speed write happens in write back? It is happening at the cache speed, and the more and more writes you do, the performance is that much different, right? Good. Now let's look at the next processor. For this guy it is good, but let's look at the next processor. This guy is not making it available for everybody. He is a sneaky guy, he keeps it himself. But if he is reading, actually this will not be hit, because the moment he is saying, that's getting into second order details, but the moment he wants to write it, he has to communicate the whole world, hey, I'm going to write it, don't get it from memory, that's called invalidate. So, but anyway, so for miss, now, where he will get data from? Because it is not here, and this is not the current data, this is stale, so where he has to functionally get it from? Now message passing started, the hardware guy has to bleed and design message passing in hardware just because you did not do in software. And you thought shared memory is write, no need of packet copy. You thought you made life for hardware engineer easy. No. You kept your software mind same, and you wanted the benefit of multiprocessor, and you did not change anything, and now hardware has to put this logic of, right? So copy, write back. You thought no movement of data in shared memory. Looks like you have brought the complexity of message passing now in hardware too, right? I see a lot of laptops again going up. Please close it down so that others don't keep opening, please. Okay? If you are not interested, that's fine. Please be role model for others who may be interested. Okay, do you see that? Are you agreeing that just because the software remained same but number of processors increased, your movement of data did not go away, right? If you had done your message passing in software, possibly only movement of data must have been there. No worry of cache coherency checkup, no snooping, no serialization in hardware. Do you agree that? Right? And you can do the miracles. You can change it and you can do the miracles. Okay, so now that's what we talk about. CPU, local cache, it is going to do later. That means now it has to do housekeeping bit saying which data is dirty, which data is not dirty, and all those things. Right? That's called dirty bit and housekeeping. So we talked about message passing. What about control? Control, the 2 bits there is a messy protocol. How many of you know it's very messy, right? And that is needed because you guys did not do simplification in life for hardware guys. And that's a write through, simple, but write back it becomes very complex. Okay, so now somebody, as is shown here, when the gentleman came, I said, why should I wait for 4? Why not I just post it, right? You see what I'm saying? Post it so it is faster than cache speed, correct? But what happens for myself? I'm the guy who posted it. And this core ran a producer. The producer posted in that posted write cycle, not even in the first level cache, not even here, right? You see what I'm saying? Not even here. He wanted to be so fast, he posted it and he went away. And now let's say he got rescheduled and now consumer came in. Now consumer wants to read it. Normally what he will read, where will read it from? Cache. But then, is this the latest one? So now data has to come. Now where are the source of data? Source of data is coming from memory, this hit, this or other CPU. You remember we talked about other CPU? Now we're talking about 4 different places data is coming from. From my own posted write buffer, or my own local cache, or my own hardware shared memory, or other person's posted write buffer, other persons. So now we are talking about the message passing increasing in dimensions. If it was done in software, possibly 1 message passing network, but now we're talking about 6 message passing network because the hardware guys wanted to do faster, because your locality was not straight, and now he brought up all this. So this is the shared memory. Now the data is moving not in 1 network. We're talking about replicating that n into n, because data has to come from local write buffer or local cache, from another write buffer or from another cache or from shared cache or from shared memory. So all these things because software did not change a dime and they want to use multiprocessing with shared memory concept, right? And hardware guys are bleeding. And you thought you will never see me again. You are seeing 6 times. Okay? So we have use cases. I'm going to start with this one. So this is software queue, producer, consumer. Right? You all do this, right? Network, producing, consuming. What policy will you use in your software? FIFO, LIFO, which one normally? Normally, just first what comes to your mind. Don't think too much. First comes, FIFO, right? Again, you are making hardware guys angry. Why? So if it's cache, we talked about locality, right? Locality. So locality, which will be in the cache? Whatever you did recently will be in the cache, or whatever you did yesterday will be in the cache. Then why do you want to go FIFO? First in, first out. Yesterday I put it in. I will go for that. Are you put it today? You take it first. So why not think some hardware based lifetime problems? Make their life easy. Okay, I'm done. Any questions? So we have much more user case studies. You will come in the afternoon before doing hands-on. So I enjoyed doing this. This was my dream. I wanted to do this all the time. So in India, I designed a parallel processor computer. There's a company called CDAC, Center for Development Advanced Computing. I was the prime architect, and our charter was to connect 1,000 nodes. And then we had each one had its own local scratch, and we had links connecting, and we designed a switch. And then the company where I am, they were asking for people who design multiprocessing, and I applied and I came. And then they said design 4 CPU system, and they said 1 memory. I said no, this is not this system I designed. I was hard to design 1,000, but this is complex because this is 1 memory. No, I'm not. So then life continued on. So I'm here now doing software because I said the hardware software are not changing. If I do the systematic multiprocessing, my life will be bad. So let me move to the problem creator space. So I'm in software now. Any questions? Any comments? Any criticism? Okay. Anything?
So actually there is a scheduled break after this. So if people have questions, go ahead and...
Okay. I'm done.
That will cut into the break, by the way.
So if I do want a favor from you all, go to now open your laptop. I will take one minute of your time, please. www.dpdk.org. The reason is, see, I am only one guy from the team, but there are people whom I admire in this team, dpdk.org. I don't know how many of you know Venki Venkatesan, right? So, he is the man for everything, whatever DPDK today is. He dreamt and he made it happen. So some of those people are on this site. I want you to get the benefit of listening to them 24/7, interacting with them 24/7. words of wisdom. You can share your wisdom and you can make changes. So www.dpdk.org and then go to development tab. It's a development tab. Click that development tab. Are you able to see that? Development. And then if you scroll down, maybe 1 or 2 paragraphs down, you will see a line ending to be registered. And the to be registered will be hyperlinked. Maybe slightly you have to go down. Are you able to see that? To be registered will be the end of the line. It will be hyperlinked. So click that, and now you will be able to be part of the team. Put your, create your own username, password. You will be part of the team. You will know what, like containers, virtualization, VPP, DPDK, multi-core, RISC, all the 6 different architectures, CPU architecture support, all the NICs, right? Whether it is Celsio, Broadcom, and then here are some gurus here sitting here who are in the beginning, earlier days. Can you just talk about DPDK? You are all the gurus, right? Just tell some 2-3 words about DPDK. What do you like and what you don't like?
Okay.
Don't like, we'll talk separately. What you like, you can talk here.
Okay. All the confidential stuff, or just
whatever they will enjoy. They are registering right now. They're trusting on my word. I appreciate them.
No word. No.
What they will like it.
Now, the partnership between Intel and 6Win, obviously, we made a good work on data plane development kit. And as you can see now, it's not just Intel, many other companies, all the other architectures are being regrouped under this, I need to say, open source project, which is now, by the way, managed by the Linux Foundation. So it's not 6Win hosted anymore, which is nice. So it's an objective framework where you can go and work. And you will see many other use cases where data plane development kit is being used, not just for POCs, but it's being deployed. We had a press release with this company called Navnear. You can see how it is being deployed in the telecom space to accelerate 4G, 5G network. So maybe, if you have complaints, don't come to me. But if you see your smartphone is getting faster and faster, when you are browsing and you are streaming videos, that could be the reason. They are just using the standard COD servers Intel based now, and with different maybe 10 gig, 40 gig, 100 gig NICs, and maybe the next ones are coming. So this framework is really open source, and I just invite everyone to go to the website. And the community is bigger now. How many people now? More than hundreds of obviously contributors that are active, which means, by the way, if we have 100 active committers, it means that we have thousands of people who are not active and just using it on the background. So that's free stuff, always.
So it's the Linux Foundation, as he's saying. So each one of you can equally impact. Go ahead.
Hi, my name is Sundar Vedantam. I have one more presentation in the afternoon to talk about, again, one particular library that's getting added to DPDK, particularly to improve performance along the same lines, talking about run to completion and pipeline and how to combine them together so you can have the cake and eat it too, kind of thing. So it's a great presentation. So I hope you all can join. There is a lot of work going on in DPDK, new libraries getting added, more and more companies joining, and the performance continuing to improve day by day. And it's an open source project, so anybody can contribute. So I hope you'll all download the code, play with it. There are so many sample applications available to get to know and put it to good use right away.
And if you're more a video person, note down this website, www.dpdksummit.com, www.dpdksummit.com. And so you'll be able to see the Venki I was talking about, 7 sins of packet processing.
Yeah, so that is also available on YouTube.
YouTube. No, the reason I'm not telling YouTube is the moment I go to YouTube, I see possibly half video, then I go into my favorite songs. so go to www.dpdksummit.com, look at a lot of architects talk about, and you will see the videos. Okay? I enjoy talking to you.
So I think we're up with the time for at least the online audience, so discussion in the room Are there any questions from the online audience? Oh, okay. So, this is for the online audience. Thank you. We will proceed with our sessions breaks here. So thank you, whoever is online, for attending. We will be the recording will be available, right? And how can they contact us if they need us?
Sure. So we'll post the slides and presentations on YouTube, SlideShare. I'll send you guys all out a note, and I'll post it also on the Meetup site, so there'll be several notifications of where you can find them.
No, this is particularly for the online.
Oh, the online audience. Check back on the Out-of-the-Box Developer Meetup page, and you'll see a posting there as far as.
They registered through the Meetup page?
They registered through On24.
Oh, okay.
Okay, so we'll send something out with a notification to you where you can find them, but they'll also be posted on the Out-of-the-Box Meetup page.
Yeah, so after this, so by the way, in case you guys didn't realize, MJ has worked with DPDK team since 2009, and he's worked at Intel from 1991, and he's in the hardware background. And how many patents do you hold, MJ? 21? Yeah, and he was awarded Intel Achievement Award in 2016, which is Intel's highest honor based on innovation and results. So yeah, that was MJ for you.